Okay, this is the continuation of building a seismic analysis for an embankment dam using FLAC. This is the third video following through this code, so you can pause the video and write the code in your own text file and then call it into the demo version of FLAC and follow along that way. Okay, so the last thing we had done is we solved for the seepage analysis here, and then we undid all the settings for the seepage analysis on these two lines, and we did a static solve here, which now we're getting closer to our final initial static stress state. Okay, so we ended on this pause. Okay, so the next thing we're going to do is, now that we have a phreatic surface, which we can see here with the pore pressures, all right, this is what our model is looking like. So what we can do is we need to assign two things. We're going to assign a saturated shear modulus to the elements that are underneath the phreatic surface, and we're going to assign a bulk modulus that is to the elements that are underneath the phreatic. We're going to assign a bulk modulus that is, quote, saturated. Now, some people might not agree with doing this, or they might not even agree with doing a saturated shear modulus, because your shear modulus is a function of your density and your shear wave velocity squared, right? Rho v squared. And which density do you use? You could use a dry density, and then it wouldn't matter. You would have one shear modulus above and below the phreatic. Or you could use the unsaturated density for a shear modulus that are above the phreatic, and a saturated density for the shear moduli that are below the phreatic. And that's what we have done. However you do it, or whatever you think is right, you can do it your way. So you can have one shear modulus for above and below for a soil, or you can break it into two. So I broke it into two here. In the end, when you're talking about deformations, it's probably not going to make that much of a difference if you're talking about big deformations. And since bulk modulus is a function of shear modulus, that's why we need to get a new bulk modulus saturated. But this is drained, right? This is not the dynamic bulk modulus. Okay, so importantly, so here's our seepage. This is our static solve after the seepage. And so we're going to use an extra grid variable. An extra grid variable, we're going to use extra grid variable number 1. Extra grid variables are kind of, you can think of them as a list. So extra grid variable 1 gets its own piece of paper. And in that list, consisting of rows, you can assign different things to it. So the extra grid variable 1, and then the first row here, this first row, is going to be assigned to this number 1, is going to be assigned is going to assign the string variable called upstream shell to the group, right? So that means that basically what we're saying is we're associating this group upstream shell, which is here, this thing, has its own string variable called upstream shell, but we're going to assign it an extra variable 1, case 1, right? So now anytime we go, all the elements within this soil group will have an extra grid variable of 1, right? And then so the extra variable 1 of the downstream shell here, I'm not doing a great job of explaining this, I apologize. You can read my FLAC practical, or the FLAC guide, it does a much better job. The extra grid variable 1 for this downstream shell is on row 2, right? So it's like the case 2 of the extra variable 1 is associated with this downstream shell, and so on. So every group gets its own number, basically, is what's happening in this code. And this is really important code because it helps out with like a lot of fish functions. All right, so we're going to use it right away. So now, and if you want to learn more about how arrays work and fish, you can read the FLAC guide. So I'm not going to get too into detail here. Basically, what we've created 2 arrays One ray is called saturated shear, and it's going to have 6 numbers in it. Think of an array as a list, one column list. And I mean, arrays can have more than one column. They can, but this is a 1D array. And the first row has this value of 2.5, and this is 2.5 for the second row, and this one is 1.69. So each row corresponds to a group. So the upstream shell saturated shear of 2.5 psf times 10 to the 6 is the saturated shear modulus of the upstream shell, and the saturated shear modulus of number 4 here group is this upstream foundation number. Okay, and then the same thing, we have another array called this B drain sat, and those contain the bulk modulus saturated shells. The bulk modulus drained saturated numbers. Okay, so you don't have to do it this way. You could just go ahead. You don't have to use arrays or fish functions. You could just come back up here and say property bulk or shear, and then put the new number in for the saturated shear, but for each element that's underneath the phreatic, and do a bulk, update the bulk. So it'd be property S equals number, B equals number, and then instead of doing it by the group, you could do it by I number, J number for the element. So that would be one way to do it, but I didn't do it that way. So what I did instead was I put all these numbers into arrays, and then I wrote a fish function to loop through this, and if the model is not null model is 1, the null soil model, every soil model has a model number. And then I say, if you're below the phreatic surface, go ahead and you get a saturated shear modulus. If you're below, you also get this bulk modulus is now a drained saturated bulk modulus, right? And so you would have, so you grab the group number for each element, and this group here, like let's say you're in the upstream shell is 1, so it's going to say the shear modulus of any element underneath the phreatic in this shell is going to get a sat shear. It's going to get the number associated with the array, so sat shear, and then this will be 1, and we know that sat shear 1 is 2.5. So that's a pretty bad explanation of what's happening, but that's what's happening, and then we end our ifs and end our loops. So between this function and this function, all we're doing is assigning saturated shear modulus and the bulk modulus. And we are going to go ahead and do that. So here's the pause. We're going to go from there to here, and we're going to solve it. So, okay. So let's look at, let's make a plot of the properties. Okay, so there's a shear modulus. Okay. So let's see if that went through. Oh, I have to do continue to actually run the code. Okay, so now these should change, right? And they did. So this is kind of where the phreatic surface is running. And so the upstream shell above has a different number than the downstream or the upstream shell below the phreatic surface. Okay, so that's how that was handled. Okay, so the next thing is we're going to do a save, and this saves it to the folder where we're working out of. And then, importantly, we're going to change the water bulk modulus to a real value of 4.18 e to the 7th psf. And this is now, we're doing this because now it's a dynamic analysis from here down. There's not another solve until the dynamic solve. So that's why we're saving here. See, it even says the name of the solve, initial static stress post seepage, right? And after we have updated the shear modulus and bulk modulus. Okay, So the next step, the next solve is a dynamic solve. So at this point, when the next solve occurs, we want the bulk modulus to be a real value. So then the load will be taken on by the water and we'll get a response, a pore pressure response. So let's go ahead and continue. Okay, and you can tell here, water bulk, that was the last thing that was read in. Okay. So the next thing, we're getting ready for the dynamic loading, as I state here. So what we're going to do is, we had it set for small strain mode. Now we're going to set it to large strain mode, and we're going to set dynamic on because it was off before. And then we're going to set some Rayleigh damping. So you can use any kind of damping you want. One choice is to use Rayleigh damping, and this is 0.2%. 0.002 is 0.2%, and we're going to use only the stiffness. We're not assigning mass Rayleigh damping, only the stiffness portion. And we're doing it at what FLAC calls a center frequency, so the frequency of 1.1 hertz. All right? And this is basically this isn't really going to damp anything out. It's just going to damp out what FLAC manual calls high frequency noise, and that's why we do it. Okay, so we're here at this pause. Okay, and then the next thing we're going to do is we're going to create a synthetic earthquake to put into this, and that ends here. So the synthetic earthquake that we're putting in looks like, oh, actually it's not here. Okay, well, it's a velocity. After we put it in, we can pull it up here. So I need to rename this. So I'm going to go edit and then name this to shear mod. Okay, now it's changed. Okay, so basically after the damping, the way we're doing this, I'm not going to really explain this because normally you would have an earthquake yourself to put in, but what this function is doing, so here it is creating a velocity input, okay? So we create a blank table. A table is just x and y points, and that's what we need for an earthquake, right? And then we put some variables in at the beginning of this function, and then we loop through, and we create a table. We create an XY table. And so we're adding and multiplying and subtracting sine waves, okay? And that gives us a velocity. And we're assuming that this is an upgoing only velocity input that has been deconvolved. So this is not a free field outcrop motion. This has not been deconvolved by shake or anything else. We're just assuming that this is a velocity that's upgoing only. Okay, because we're gonna change it to a stress here, a stress input. But we need to create the velocity first. So let's go ahead and do that. This is kind of a lot here. If you don't have an earthquake motion, just feel free to copy this exactly, and you'll get something that will load the system. Okay, so we're going from this pause on 312 to this pause here. So we're going to continue. Okay, so nothing should have changed with the model, right? Because right now we're not dealing with the model. We're dealing with this input. So let's look. So this has been stored as history number 100. So let's look at, if we go plot history and then look for history 100. Oh, it's not on there yet. Yeah, okay, it hasn't shown up yet. That's okay. I think it's because it's a table. Let's see. Yeah, there it is. We haven't converted to a history yet. It's just in table format. And so we're going to call it velocity input. And I don't want the crosses. I want a line. The crosses are x's. Okay, so here's what our upgoing velocity. So this is just basically this right here. You can do this in Excel too if you want to see what this thing looks like. It's just, here's our velocity input. So it's, if you look hard enough, you can find a pattern, but because there's not that many frequencies in there. Okay, so there we go. That's our input motion. And now the next thing we're going to do, let's see, is, okay, so the next step is to take this velocity here, which is shown here, and we're going to convert it into a stress. And the way that you convert it into a stress is with this command on line 352. So this is an apply command, so we're going to apply a stress input to the bottom of the base here, and that's why this is J equals 1. So this says apply, and then SXY is shear stress, so we're going to apply a shear stress of with this thing called the stress multiplier, and we're going to apply the history of this table 100. So table 100 is the velocity, and we're converting it to a history. So there's a lot going on here in this line. You're converting the table of the velocity to a history here, and you're applying it to the bottom of the model. And before you apply it, you're converting it from a velocity to a history by multiplying it by this number. So 16870 space history, that is actually, FLAC takes that as being multiplied, right? It's just multiplying each velocity point by this number, which makes it a history. Which makes it a stress. And it's a history too. So the way we came up with 16870 is to take 2 times the rho of the bedrock, the density, times the VS of the bedrock. So we're only applying a horizontal loading, SXY. So that would be 2 times whatever the number was, around 4, and then times the VS, whatever number that was, which was maybe 2,000. I don't know. It's in the property table. So let's see, 2 times 4 times 2,000 is about 16,000. So that's basically where this number came from. And if you were applying a vertical motion, you would apply SYY here with a different stress multiplier. Okay, and also I want to point out that this 2 is being multiplied by rho. And the 2 comes from the fact that this is a deconvolved motion, right? So this is a motion that's an upgoing only velocity and is deconvolved. If you were putting a free field motion in directly, a bedrock outcrop free field motion, you do not need to do this. But this also assumes that you have a quiet boundary condition on the bottom, which is what we do in the next step. All right, so that's a very specific thing. Upgoing only velocity, quiet boundary condition on the bottom, not a free field bedrock outcrop motion. And more information on that is definitely in the FLAC guidebook because it can get pretty confusing. But this is correct. This is the one correct way to do it. Okay, so the next thing is we are going to apply the free field, and this apply FF tells FLAC to apply free field boundary conditions on the ends, so this end and this end. You don't have to include an IJ grid for the numbers for the grid point, which is nice. And we're going to apply an X quiet and a Y quiet boundary to the J equals 1, and the J equals 1 is here. And I never showed you guys this. Let's look at grid points. So this is the grid point for each. Here's the number for each grid point. 1.1 is here, 2.1. So J equals 1. 1 J is the second number, so all the ones with J equals to 1. So that's what's going on there. Okay, so let's go ahead and do that. Continue. Okay, so it applied everything here. And I don't think it'll change. Oh, it did change it. So there we go. So free field on the end, quiet on the bottom. It's no longer fixed. It does have the seepage pore pressure or boundary conditions in there still. That's okay. And then the last step here, before we start solving it, is you can do the set step. So set step, and then I made it a really large number. This tells FLAC to how many steps are going to happen before FLAC stops on its own between each solved dynamic time. So if you solve this thing for 0.5 seconds, who knows how many steps it'll take? We're already at step 23,000. So this line here is saying that you have to get to 100 billion or whatever this number is before FLAC will stop. So that means between each of these, so from 0 seconds to 0.5 seconds, you have at least this many steps before FLAC stops. And same with here, between half a second and 5 seconds, it has the same number. But this is such a big number that it's never going to stop on its own, right? So that's you do this because the default is kind of a low number. Okay, and then here we are resetting any movement that happened in the x velocity and the y velocity and the displacements of every grid point in the model to 0. Now this is, you don't have to do this, you can, but now this ensures that anything that we track starts from 0. If we didn't do this, you might get like a very small displacement added to your displacement for your final number. A small displacement that came from any movement with the static solves, right? So if we're going to go from this pause to this pause, so we're going to run through 0.5 seconds of dynamic time, okay? And we are going to, before we do that, we're going to plot up the velocities vectors. Let's see, where's velocity? Vector, velocity, and I usually make them blue. Okay, so right now it's 1.5 times 10 to the 8th, -8th feet per second. So it looks dramatic with the arrows, but it's basically 0. And if I hit continue, we're going to run through some time, and if I hit automatic, so as you can see, these are changing. The velocity is changing very slowly. We're at 0.1 seconds, problem time, and the velocity vectors are going to the left. And so this is one way to track what's going on with the velocities. And here's the max vector, 3.3 times, so 0.3 feet per second. You know, this is an earthquake loading, so you would expect some substantial movement. You can get much higher too. And we're almost at a half a second, and it should pause. Let's let it run. Okay, so now this is what it looks like at a half a second. So to continue this, we're going to go through solve dynamic time 5 seconds, and then we're going to go to 8.3 seconds. And I chose 8.3 because that's where the velocity basically zeroes out. And you could go farther if you wanted, but this gets the point across. There's a little bit of deformation at this point. And so I'm going to hit continue, and I'm not going to solve this all the way on this video because it would take too long, but I think we'll show a video possibly with showing some of the results. But I think it's about a foot of vertical deformation that this turns out to be. We can track the y displacement versus time of the crest y displacement. So let's see what that looks like. So you can see this is time on the bottom, and it's bouncing around. Very small displacement up here, but it's going negative, right? It's moving down. So, okay, that's it.